Right now, without any sensation of it at all, you are moving in at least 4 different ways at once, and the fastest of those motions is carrying you through space at more than 600 kilometers every second. You cannot feel a single one of them, because for most of human history there was nothing to measure them against. That changed only once astronomers found a fixed backdrop faint enough, and old enough, to hold still. The leftover light of the Big Bang itself. Reading the tiny distortions in that ancient glow, scientists worked out that the Milky Way, our entire home galaxy of some 200 billion stars, is being pulled across the universe toward a destination it cannot see, and we are only beginning to map. Getting to that answer took nearly a century of patient work. A pendulum in a Paris basement that proved the ground itself turns, a lucky pair of engineers who stumbled onto the oldest light in existence while trying to fix a radio antenna, and a survey of galaxy motions large enough to redraw the Milky Way's address in the universe. This account traces that pull outward, one layer at a time, the spin of the Earth, the orbit of the Sun, the turning of the galaxy itself, and the vast, largely invisible structures now dragging all of it toward a single distant point in the sky. Begin with the simplest motion there is, the one built into the ground itself. Earth turns on its axis once every 24 hours, and because the planet is a sphere roughly 40,000 kilometers around at the equator, a point standing on that line is being carried through space at close to 1,670 kilometers per hour, faster than most commercial aircraft. Move away from the equator toward either pole, and that speed drops because you are tracing a smaller circle in the same 24 hours. Stand exactly at the north or south pole and your speed from spin alone falls to almost nothing, even though you are still turning once a day like everyone else. This is the first lesson of the whole subject. Speed through space depends entirely on what you are measuring it against, and the choice of that reference point changes the number completely, without changing anything real about the motion itself. For a very long time, nobody could prove any of this directly, because the spin of a sphere produces no sensation anyone standing on its surface can feel. The air, the ground, and every object around you turn together at the same rate, so there is nothing nearby to compare your own motion against. The first direct mechanical proof that the ground really is turning came only in 1851, when the French physicist Léon Foucault suspended a heavy pendulum from the ceiling of the Pantheon in Paris and set it swinging. Over the course of a day, the plane in which the pendulum swung appeared to rotate slowly across the floor, even though nothing was pushing it sideways. The pendulum itself was simply continuing to swing in a fixed direction relative to the wider universe. The floor beneath it, and the building, and the city, were the things actually turning underneath it. It was, for many observers who watched it happen, the first time the Earth's rotation had been made visible, rather than merely calculated. Layer a second motion on top of the first. While Earth spins, it is also circling the Sun, tracing a nearly circular path some 150 million kilometers out, a distance astronomers call an astronomical unit and use as a convenient yardstick for the solar system. One full circuit takes 365.25 days, and to cover that distance in that time, Earth has to travel at roughly 107,000 kilometers per hour, more than 60 times faster than its own spin at the equator, and considerably faster than a rifle bullet leaving its barrel. Neither of these speeds is felt by anyone standing on the surface, for the same reason a passenger on a smooth flight does not feel the aircraft's speed. Everything around you is moving together at the same rate, so there is no relative motion to sense. Confirming that Earth genuinely orbits the Sun, rather than the reverse, took even longer than proving its spin. The decisive evidence came from stellar parallax, the tiny apparent shift in a nearby star's position against more distant background stars as Earth moves from one side of its orbit to the other, 6 months apart. Because even the closest stars are so far away, this shift is extremely small, and it was not successfully measured until 1838, when the German astronomer Friedrich Bessel detected it for a star called 61 Cygni, finally putting a direct, measured number on the scale of Earth's orbit and confirming, beyond any reasonable doubt, that the ground people had always trusted as fixed was in fact hurtling through space on 2 overlapping paths at once. Those 2 motions, the daily spin and the yearly orbit, are only the beginning. The Sun that Earth orbits is itself moving, carrying the entire solar system along a third and far larger path, an orbit around the center of the galaxy that contains it. That orbit is so vast and takes so long to complete that no human civilization has existed for even a small fraction of a single circuit. Untangling it required evidence drawn not from watching planets cross the sky, but from the structure and motion of the stars that share the galaxy with the Sun, and from patient measurement of how their positions creep, almost imperceptibly, against the fixed backdrop of more distant galaxies. What emerges from that evidence is a picture with the Sun as a single pale point of light among roughly 200 billion others, all bound together and all in motion, tracing out one enormous rotating structure. Understanding what that structure is, how fast it turns, and why it holds together at all, is the next layer to peel back. The Sun sits roughly 26,000 light-years from the centre of the Milky Way, out in one of the galaxy's spiral arms, a region sparse enough that no other star lies closer than about 4 light-years away. From that position, the Sun is orbiting the galactic centre at a speed of roughly 230 kilometres per second, which works out to more than 800,000 kilometres per hour, dwarfing the 107,000 kilometres per hour of its orbit around the Sun that Earth itself completes every year. At that speed, one full circuit of the galaxy still takes approximately 230 million years, a length of time astronomers sometimes call a galactic year, because the distance being covered is so enormous. To put that span in human terms, the last time the Sun was at its current position in its galactic orbit, the earliest dinosaurs had not yet appeared on Earth. The Sun has completed only about 20 such circuits since the solar system itself formed 4.6 billion years ago. What is actually at the centre of this orbit, the point all of it is turning around, is itself remarkable. At the very core of the Milky Way sits a supermassive black hole named Sagittarius A star, with a mass around 4 million times that of the Sun. Confirming that mass, and confirming that an object this dense really was sitting there at all, took decades of watching a handful of individual stars race around it on tight, fast looping orbits, work led independently by 2 research teams, one under the astronomer Reinhard Genzel in Germany and one under the astronomer Andrea Ghez in the United States, both tracking the same small cluster of stars for years at a time using the largest telescopes available. Their combined results were precise and consistent enough that the 2 of them shared the 2020 Nobel Prize in Physics for the discovery. Contrary to a common misconception, this black hole is not actively pulling in everything around it like some cosmic drain. Most of the galaxy's stars, including the Sun, orbit it at a safe distance in stable paths, held in place by gravity in exactly the same way. Earth is held in a stable orbit around the Sun, rather than falling into it. The black hole's gravity matters enormously to objects that pass very close to it, but at 26,000 light-years away, its influence on the Sun's orbit is simply the ordinary pull of a very large mass at the centre of a very large system. What actually keeps that whole system turning together, though, does not add up using only the visible stars. If the Milky Way's mass consisted only of the stars, gas, and dust astronomers can directly observe, then stars far from the centre should orbit noticeably slower than stars close in, following the same pattern seen in the solar system, where distant Neptune moves far more slowly than nearby Mercury. Instead, when the American astronomers Vera Rubin and Kent Ford measured the orbital speeds of stars and gas clouds at different distances from the centres of dozens of spiral galaxies during the 1970s, they found something unexpected. The speeds stay roughly flat far out into a galaxy's outer reaches, almost as if a great deal of unseen mass extends well beyond where the visible disk of stars ends. Their work, confirmed and extended by many later surveys, is one of the strongest pieces of evidence for dark matter, a form of mass that does not emit or absorb light, and so cannot be seen directly, but whose gravity is unmistakably present in how galaxies actually spin. Current models suggest the Milky Way sits inside a roughly spherical halo of dark matter several times wider than the visible disk of stars, and that this invisible material outweighs all the galaxy's stars, gas and dust combined by a wide margin. Nobody has directly detected a particle of it. Its presence is inferred entirely from motion, from the simple fact that the galaxy is spinning in a way its visible mass alone cannot explain. That detail matters for everything that follows, because gravity, including the gravity of matter nobody can see, is exactly the force responsible for the larger motions still to come. The drift of entire galaxies toward each other, and the eventual collision that will reshape the very disk the Sun now calls home. Picture the Milky Way from far outside it, a vantage point no human has ever actually had. but one astronomers can reconstruct with confidence from the way its light and motion behave from the inside. What emerges is a flattened disk roughly 100,000 light-years across, and only about 1,000 light-years thick at the Sun's location, shaped less like a solid wheel and more like two fried eggs pressed back to back, with a dense bulge of older stars at the center and a thin star-filled disk spreading out from it in sweeping spiral arms. Astronomers classify galaxies of this general shape, a flat rotating disk with a central bulge and spiral structure, as spiral galaxies, one of the handful of broad categories first laid out by Edwin Hubble in the 1920s and still used today. Embedded in the Milky Way's disk are somewhere between 100 and 400 billion stars, a range this wide because counting stars across an entire galaxy from inside it, with gas and dust blocking huge stretches of the view, is genuinely difficult. Astronomers hedge the exact figure while remaining completely confident in the overall structure. The spiral arms themselves are not fixed rivers of the same stars flowing around forever. They are more like traffic jams of density moving through the disk, regions where gas and stars temporarily bunch up as a wave of increased gravity sweeps around the galaxy, triggering new star formation as it passes, before the individual stars carry on past that region and disperse the way individual cars pass through a slow patch of highway traffic without staying in it forever. The Sun has passed in and out of spiral arms many times over its 4.6 billion year history, without that passage causing any dramatic disruption to the solar system. Wrapped around this entire visible structure, disk, bulge and spiral arms together, is the dark matter halo introduced in the previous chapter, extending, by current estimates, roughly 300,000 to 600,000 light-years out from the center, several times wider than the visible disk itself. That halo is not a thin shell. It is thought to be a diffuse, roughly spherical cloud of mass, thinning out gradually rather than stopping at a sharp edge, and it is this halo's gravity, far more than the combined pull of every visible star, that holds the outer galaxy together and governs how fast everything within it orbits. Without it, the outer stars of the Milky Way's disk would fly apart entirely, unable to complete a stable orbit at the speeds actually observed. The Milky Way is not unique in this respect. Every large spiral galaxy studied in enough detail since Rubin and Ford's original work shows the same signature, visible matter that cannot on its own account for the observed rotation. This consistency across galaxies of many different sizes, in many different parts of the sky, is part of why dark matter is treated as a serious component of the universe rather than a patch invented to explain one anomaly. Current estimates put ordinary visible matter, stars, planets, gas and dust, at only about 5% of the universe's total mass and energy, with dark matter making up roughly another 27%, and the remainder attributed to the dark energy discussed later in this account. It also means that when astronomers describe the mass of the Milky Way, the figure that matters for questions about motion and gravity, including everything discussed in the chapters ahead, is not just the mass of its stars but the mass of this much larger, largely invisible halo surrounding them. That combined mass is what the Milky Way brings to every gravitational interaction it takes part in, its pull on smaller satellite galaxies nearby, its slow gravitational dance with its nearest large neighbour, and eventually its role in a collision that will unfold over billions of years. Before any of that can be traced, though, there is a more basic question to answer. If the ground, the Sun, and now the galaxy itself are all in motion, what is actually still enough to measure any of it against? The answer turns out to lie not nearby at all, but in the oldest light in the entire universe. Every motion described so far, Earth's spin, its orbit, the Sun's circuit of the galaxy, was measured against something else that was itself moving: the ground, the Sun, the galactic center. To find a motion that is not relative to some other moving thing requires a reference point close to truly fixed, and the closest astronomers have ever found is a faint bath of radiation filling the entire universe called the cosmic microwave background. This radiation is the leftover glow from a time, roughly 380,000 years after the Big Bang, when the universe had cooled enough for light to travel freely for the first time, rather than being scattered constantly by a dense hot fog of charged particles. It was discovered almost entirely by accident in 1965 when two radio astronomers, Arno Penzias and Robert Wilson, working with a sensitive antenna at Bell Labs in New Jersey, kept detecting a faint, uniform hiss of radio static that would not go away, no matter which direction they pointed the instrument or how carefully they cleaned pigeon droppings out of it. What they had found, working independently of a nearby team of physicists actively predicting exactly this kind of leftover radiation, was the afterglow of the Big Bang itself, work that earned Penzias and Wilson the 1978 Nobel Prize in Physics. That light has been stretching and cooling ever since, as the universe itself has expanded, and today it arrives from every direction in the sky as extremely faint microwave radiation corresponding to a temperature only a few degrees above absolute zero, the theoretical coldest possible temperature. Because this radiation originated so early and so uniformly, and because it fills the entire observable universe rather than coming from any single object, it acts as the closest thing to a universal rest frame, a backdrop essentially standing still relative to the universe as a whole. Later, more sensitive instruments, beginning with a NASA satellite called COBE launched in 1989, mapped the temperature of this background radiation across the whole sky in far greater detail, and found it was almost perfectly uniform but not quite. It appears very slightly hotter in one direction of the sky and very slightly cooler in the opposite direction, a pattern called the dipole. This is exactly the pattern you would expect to see from a moving observer looking at a stationary field. Light coming from the direction you are moving toward gets compressed to slightly higher energy, an effect called a Doppler shift, the same phenomenon that raises the pitch of a siren approaching you and lowers it as it moves away, while light from the direction you are moving away from gets stretched to slightly lower energy. By measuring the exact size and direction of this hot and cold pattern, astronomers can calculate precisely how fast and in which direction the observer, meaning Earth, the Sun, and the whole local group of galaxies around them, is actually moving relative to that nearly still cosmic backdrop. The measured answer is striking. The local group, the small cluster of galaxies that includes the Milky Way, is moving at roughly 630 kilometers per second, well over 2 million kilometers per hour, toward a region of sky lying across the constellations of Centaurus and Hydra. This is dramatically faster than the Sun's 230 kilometer per second orbit around the galactic center, and it is a motion the orbit around the galactic center cannot explain on its own. The galactic orbit only accounts for the Sun's movement within the Milky Way, not the movement of the entire galaxy through the wider universe. Something else, something acting on the scale of the local group as a whole rather than on any single galaxy within it, has to be responsible. Finding out what that something is means looking past the Milky Way's own stars and its nearest neighbour entirely, out to gravitational structures far larger than any single galaxy, the subject the next several chapters exist to trace. The Milky Way does not sit in isolation. It belongs to a loose gravitational grouping called the local group, a collection of roughly 80 known galaxies spread across a region of space about 10 million light-years wide, bound together by their mutual gravity rather than drifting apart independently. Of those 80 or so galaxies, the overwhelming majority are small, faint dwarf galaxies, some containing only a few million stars, easily overlooked next to the two giants that dominate the group entirely. The Milky Way itself and a spiral galaxy called Andromeda, roughly the Milky Way's twin in size and structure, sitting about 2.5 million light-years away. Andromeda is, remarkably, visible to the naked eye under a genuinely dark sky, appearing as a faint elongated smudge in its namesake constellation, the single most distant object most people will ever see without a telescope. A third significant spiral, the Triangulum galaxy, orbits somewhere near this pair, smaller than either but still substantial, while every other member of the local group is a dwarf galaxy caught in the gravitational orbit of one of these three larger systems, in much the same way moons orbit planets. The Milky Way itself keeps a retinue of these smaller companions close by, most visibly the Large Magellanic Cloud and the Small Magellanic Cloud, two irregularly shaped dwarf galaxies, bright enough to be seen with the naked eye from the southern hemisphere, currently orbiting the Milky Way at a distance of roughly 160,000 light-years. A far smaller dwarf, the Sagittarius dwarf galaxy, is presently in the process of being torn apart and absorbed by the Milky Way's gravity, its stars stretched into a long stream that loops repeatedly through the disk, a slow-motion absorption already well underway and expected to finish over the coming few billion years, a preview, on a much smaller scale, of the larger collisions still to come. This entire grouping moves together, more or less, as a single unit through the wider universe, which is exactly why the 630 km per second motion measured against the cosmic microwave background in the previous chapter is described as a motion of the local group rather than of the Milky Way alone. The Milky Way's own orbital motion within the local group is comparatively small, next to the shared motion carrying the entire group along together. What holds a structure this large together, spread across 10 million light-years, is the same force responsible for every motion covered so far: gravity, in this case the combined gravity of the Milky Way, Andromeda, and every smaller galaxy between them, along with a considerable amount of dark matter, distributed through the space they share. A useful comparison for scale is a swarm of bees. Individual bees move in seemingly chaotic paths, darting in different directions at different speeds, but the swarm as a whole still drifts together in one general direction, held loosely together by their collective behavior rather than by any single controlling force. The local group behaves similarly. Individual galaxies, including the two giants, have their own orbital motions relative to each other, but the group as a whole is also being carried along by larger-scale gravity acting on it from outside. That outside gravity is not coming from within the local group itself. Something considerably more massive, sitting well beyond the boundaries of this 10 million light-year grouping, is exerting enough pull to move an entire cluster of dozens of galaxies at over 2 million kilometers an hour. Locating that something and figuring out what it actually is occupied astronomers for decades, and the search led to one of the stranger and more evocative names in modern astronomy. A place they could measure the pull of, long before they could actually see what was causing it. In the early 1970s, astronomers analysing the motions of galaxies well beyond the local group noticed something that did not fit a simple, uniform expansion of the universe. Groups of galaxies in a broad region of the sky were moving with an extra component of velocity, a common drift, all pointing roughly toward the same distant area, as if something massive were pulling on all of them simultaneously. By the 1980s, a team of astronomers studying this shared motion in detail, working from redshift surveys of thousands of nearby galaxies, gave that unseen source of gravity a name that stuck: the Great Attractor. Estimates place it roughly 250 million light-years from the Milky Way, in the same general direction as the cosmic microwave background dipole, introduced 2 chapters ago. Across the constellations of Centaurus and Hydra, strong evidence that the local group's own drift and this larger regional flow are connected pieces of the same underlying structure. For years, actually confirming what the Great Attractor was proved unusually difficult, for a very specific reason. It lies almost directly behind the flattened disk of the Milky Way as seen from Earth, in a region of sky so thick with the galaxy's own stars, gas and dust that visible light from anything beyond it is almost completely blocked. Astronomers call this obscured strip of sky the zone of avoidance, and for decades it left a genuine blind spot in extragalactic surveys, a section of the universe that optical telescopes simply could not see through. Progress came from switching to wavelengths of light the Milky Way's dust does not block as effectively, particularly X-ray and infrared observations, including data from the 2-micron all-sky survey, an infrared mapping project completed in the early 2000s that was specifically able to peer through the obscuring disk and begin mapping what lay beyond it. What these surveys found was not a single monstrous object, but an unusually dense concentration of galaxy clusters, an entire supercluster's worth of matter clumped together in that hidden region, with a massive cluster of galaxies called the Norma cluster sitting near the middle of the densest part. The Great Attractor, in other words, is not one thing so much as a genuine crowd, a real overdensity of galaxies and dark matter large enough that its combined gravity measurably redirects the motion of galaxy groups tens of millions of light-years away, the local group among them. It is worth being honest about the limits of this picture, because so much of the relevant sky remains difficult to observe even with modern instruments. Some of the details of the Great Attractor's exact mass and precise boundaries are still debated among astronomers, and later surveys suggested that the Great Attractor itself might be part of an even larger structure pulling on it in turn. What was not in doubt, once the X-ray and infrared surveys came back, was that the drift measured in the oldest light in the universe had a real, physical cause. An actual concentration of mass hidden from ordinary sight by the accident of the Milky Way's own orientation, but perfectly detectable through its gravity. Confirming that the Great Attractor was real, rather than a statistical artifact, was only the beginning of the story though, because a much larger survey effort was still to come. one that would place the Great Attractor itself inside a structure larger than anyone had previously mapped. For most of the 20th century, astronomers organized the universe into a nested set of addresses, not unlike a postal address for a house. The Milky Way sits within the local group. The local group sits near the edge of a larger structure called the Virgo Supercluster, named for the massive cluster of galaxies at its center, and the Virgo Supercluster was understood to be one of many such superclusters scattered across the universe. This picture worked reasonably well, but it relied on drawing supercluster boundaries mainly by mapping, where galaxies appeared clustered densely on the sky, a method that can miss the underlying gravitational structure connecting regions that look separate from Earth's vantage point, but are actually part of the same larger flow. In 2014, an international team of astronomers led by Brent Tully proposed a fundamentally different way to define these boundaries, based not on where galaxies happen to sit, but on how they are actually moving. Every galaxy in the universe has two components to its motion: the general stretching of space itself, called the Hubble flow, which carries galaxies apart from each other as the universe expands, and a second, smaller component called peculiar velocity, the extra motion caused specifically by the gravitational pull of nearby mass, exactly like the pull responsible for the Great Attractor and the cosmic microwave background dipole. By carefully mapping the peculiar velocities of tens of thousands of galaxies across a vast volume of space, using a large redshift survey called cosmic flows, the team was able to trace out actual basins of attraction, regions where every galaxy's extra motion flows toward a shared central point, in much the same way rain falling anywhere within a river's drainage basin eventually flows toward the same river mouth. Using this method, they identified an enormous basin of attraction spanning roughly 500 million light-years and containing the mass of around 100,000 large galaxies, including the Milky Way, Andromeda, the entire local group, and the Virgo Supercluster, once thought to be its own separate structure. They named this newly identified supercluster Laniakea, a word combining Hawaiian terms roughly meaning immense heaven, chosen to reflect both its scale and the culture of the astronomers who led the discovery. Under this new map, the Milky Way's old address changed. Rather than sitting within the Virgo Supercluster as a distinct entity, the Milky Way now sits near the outer edge of Laniakea, with the Virgo Supercluster understood as merely the inner portion of this much larger structure, and the Great Attractor identified as sitting near, though evidently not exactly at, the true gravitational center of the whole basin. This is not simply cataloguing trivia. Laniakea represents the actual gravitational neighborhood the Milky Way belongs to on the largest scale, where gravity still meaningfully organizes matter into a coherent connected flow, the scale at which the individual pulls of countless galaxy clusters combine into one shared current, carrying everything within it, the Milky Way included, in a broadly common direction. And even Laniakea, vast as it is not the final word. The same peculiar velocity surveys that revealed it also detected an even larger scale flow, suggesting Laniakea itself may be gravitationally drawn toward a still more distant and more massive structure called the Shapley Supercluster, a genuinely enormous concentration of galaxy clusters roughly 650 million light-years away, first catalogued decades earlier by the astronomer Harlow Shapley. Whether that even larger structure is itself moving towards something else again remains, honestly, beyond what current observations can confirm. At some scale, the search for what pulls on what begins to run up against the limits of how much of the universe can be mapped at all. What is well established is more than enough to answer the question this exploration set out with. The Milky Way's motion is not a single mystery but a nested set of them, each layer explained by the gravity of something larger, from the Great Attractor to Laniakea to, possibly, Shapley beyond it. Every motion traced so far, the pull of the Great Attractor, the flow toward Laniakea's basin, the possible drift towards Shapley beyond it, is a story about gravity winning, about mass pulling other mass toward it across enormous distances. But gravity is not the only force shaping how galaxies move relative to each other, and understanding the Milky Way's true trajectory requires reckoning honestly with the other side of that contest, the expansion of space itself. In the late 1920s, astronomer Edwin Hubble, working with observations of distant galaxies and building on earlier measurements by Vesto Slipher, discovered that nearly every galaxy beyond the local group appears to be receding from the Milky Way, and that more distant galaxies recede faster than nearer ones, in direct proportion to their distance, a relationship now known as Hubble's law. The explanation that emerged, confirmed and refined over the following decades, is not that galaxies are flying apart through space like fragments from an explosion, but that the space between them is itself stretching, carrying galaxies apart, the way dots painted on the surface of an inflating balloon move apart as the balloon expands, without any single dot actually moving across the balloon's surface. This stretching, called the Hubble flow, applies to the universe as a whole and grows more significant the farther apart two galaxies are, precisely because there is simply more space between them to stretch. Here is the essential subtlety that resolves an apparent contradiction. On small scales, where two galaxies are close enough together that their mutual gravity is strong, relative to the stretching of space between them, gravity wins decisively, and the galaxies remain bound together rather than drifting apart. This is exactly the situation within the local group. The Milky Way and Andromeda are close enough and massive enough that their gravitational attraction to each other comfortably overwhelms the extremely modest stretching of the small amount of space directly between them, which is why, rather than receding from the Milky Way like almost every other galaxy in the universe, Andromeda is instead approaching it, a detail the next chapter takes up directly. The same logic holds at the larger scale of Laniakea. Within the supercluster's basin, gravity remains the dominant organizing force, gathering matter into flowing streams and dense clusters even as, on a truly cosmic scale, the space between separate superclusters continues to stretch apart. It is really only at the very largest scales, distances well beyond any single supercluster, that the expansion of space decisively overwhelms gravity's ability to hold structures together, and this is where a further complication enters. Since the late 1990s, astronomers have known that the rate of this expansion is not constant but is actually accelerating. That discovery came from two independent teams, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rias, both studying a particular kind of exploding star called a Type 1a supernova, whose intrinsic brightness is well understood, which lets astronomers use them as reliable distance markers across billions of light years. Both teams found distant supernovae dimmer, and therefore farther away, than a constant rate of expansion would predict, evidence that the universe's expansion has been speeding up rather than coasting or slowing down, a discovery that earned all three astronomers a share of the 2011 Nobel Prize in Physics. The cause of that acceleration is attributed to a poorly understood component of the universe named dark energy, currently estimated to make up roughly 68% of the universe's total energy content, though its underlying nature remains one of the most significant open questions in all of physics. Astronomers can measure its effect precisely without yet fully explaining what it is. The practical consequence of an accelerating expansion is straightforward, even if its cause is not. As time goes on, the boundary at which the stretching of space begins to overpower gravity's pull will not stay fixed, and structures that are only loosely bound today may eventually be pulled apart by that stretching, even as tightly bound structures like the local group remain gravitationally intact. This is the real tug-of-war the Milky Way exists inside, bound tightly enough to its nearest neighbours that gravity is winning decisively in the near term, while riding, at the very same time, inside a universe whose overall fabric is stretching apart faster with each passing billion years. Nowhere is that near-term gravitational victory more dramatic, or more consequential for the Sun's own eventual fate, than in the approach of the one galaxy close enough, and massive enough, to be genuinely bound to the Milky Way rather than merely nearby. Of everything discussed so far, this is the single most direct and best measured motion involving the Milky Way's nearest large neighbour. Andromeda is approaching the Milky Way at roughly 110 kilometres per second, a figure derived from measuring how its light is shifted toward shorter, bluer wavelengths as it moves toward us. The mirror image of the redshift used to measure most other galaxies receding from us elsewhere in the universe. For decades, astronomers knew Andromeda was closing the distance, but could not determine whether it was approaching head-on, or whether it might instead sweep past the Milky Way at an angle, missing a direct collision, the way two ships can pass close by without striking each other. Resolving that question required measuring not just Andromeda's motion toward us, but any sideways motion across the sky as well, a motion so subtle it took repeated, extraordinarily precise observations, spread over several years, using the Hubble Space Telescope to detect. Those measurements, published in 2012, found that Andromeda's sideways motion is small enough that a direct collision with the Milky Way is in fact the most likely outcome, with current models placing the first close encounter between the two galaxies roughly 4 to 5 billion years from now. It is worth being precise about what a galaxy collision actually involves, because the word collision suggests something far more violent at the level of individual stars than what will really happen. Stars within a galaxy are spaced so far apart relative to their own size that the chance of any two individual stars actually striking each other during the entire merger is, by most calculations, close to zero. If the Sun were shrunk to the size of an orange, its nearest neighbouring star would still be roughly 2,400 kilometres away on the same scale, an amount of empty space that makes a direct stellar collision astronomically unlikely even as two entire galaxies pass through each other. What will collide, and collide dramatically, are the vast clouds of gas and dust each galaxy carries, material dense enough and interactive enough that the encounter is expected to compress large regions of it suddenly, triggering intense new bursts of star formation across both galaxies, entire generations of new stars born in the shock waves of the encounter. The two galaxies will not simply merge in a single pass either. Current simulations, including detailed modelling work carried out by astronomers at the Space Telescope Science Institute, describe a much longer process. An initial close pass, followed by the two galaxies swinging apart again under their own momentum, then a second and eventually a third closer pass, each one bleeding away orbital energy through gravitational interactions, until the two systems finally settle into a single merged galaxy, a process expected to take several billion years beyond that first encounter to fully complete. What eventually results is thought to be a large elliptical galaxy, structurally quite different from either of the flattened spiral disks that formed it, sometimes informally referred to by astronomers as Milky, a term that has not caught on in formal usage but captures the outcome well enough. Not a destruction of either galaxy, but a genuine merger into something new. Andromeda itself is thought to carry a mass comparable to, and by some estimates somewhat greater than, the Milky Way's own, including its stars, gas, and its own dark matter halo, which is part of why the coming merger is expected to be a genuine combination of near equals, rather than one galaxy simply absorbing the other outright, the way the Milky Way is presently absorbing the far smaller Sagittarius dwarf. This is exactly the payoff for the flat spinning disk introduced back in the third chapter. As a picture of the Milky Way from outside, that disk shape, stable and recognizable for billions of years, is not the galaxy's permanent form, only its current one, already scheduled for a dramatic and well-understood reshaping. What happens to a single ordinary star like the Sun, caught up in an event of this scale, and to any planet still orbiting it when the encounter begins, is the natural next question, and the honest answer turns out to be considerably less alarming than the scale of the event might suggest. Given the scale of two entire galaxies colliding, the fate of one particular star, our own Sun, might seem impossible to predict with any confidence. In fact, this is one of the more reassuring results to come out of detailed simulations of the merger, precisely because of the point raised in the previous chapter: the vast, near-total emptiness of space between individual stars. Current models suggest the Sun has an extremely high probability of surviving the entire event without any direct disturbance from a stellar collision, since the odds of the Sun's own path, intersecting closely enough with another star to disrupt its orbit, are vanishingly small even across the many close passes required for the full merger to complete. That does not mean nothing will change from the Sun's local perspective. During each close pass between the two galaxies, the gravitational interaction is expected to disturb the Sun's orbit within the newly forming, merged galaxy, likely flinging it onto a different orbital path than the fairly orderly circuit it currently follows around the Milky Way centre, possibly farther out into the merged galaxy's outer regions, and likely on a path considerably less tidy than a simple circle. Whatever new orbit the Sun ends up on, though, its planets are expected to remain in their existing orbits around it, essentially undisturbed, protected by exactly the same enormous ratio of empty space to solid matter that protects the Sun itself from a direct stellar collision. The most dramatic changes will happen not to any orbit but to the sky itself. Simulations suggest that during the actual encounters, Andromeda will grow from a faint smudge, visible only under dark skies today, into a sprawling, brilliant structure spanning a significant portion of the visible sky, its own spiral arms and central bulge visibly distorted by the gravitational stresses of the interaction, as the two galaxies' shapes warp under each other's pull before the whole system eventually settles into the smooth elliptical shape described in the previous chapter. New star formation triggered by colliding gas clouds is expected to light up substantial regions of both galaxies with young, hot blue stars, some of which will burn through their fuel and end their lives as brilliant supernovae, within a relatively short cosmic timescale of only tens of millions of years, adding a scattering of dramatic transient events to an already spectacular sky. There is a longer-term consequence worth naming as well, one that unfolds on a timescale even beyond the several billion years required for the visible merger itself to complete. Each of the two original galaxies carries a supermassive black hole at its center, Sagittarius a star at the heart of the Milky Way, and a comparably massive black hole at the heart of Andromeda. As the merger proceeds and the two galaxies' matter settles into a single structure, these two central black holes are expected to sink toward the new combined center under the pull of dynamical friction, a process that transfers orbital energy to surrounding stars and gas, eventually spiraling close enough together to merge into a single, even larger black hole, likely releasing a substantial burst of gravitational waves in the process, ripples in space itself of exactly the kind first directly detected by observatories on Earth in 2015, in an unrelated but comparable event. Two much smaller black holes, each tens of times the mass of the Sun, merging in a distant galaxy and sending a detectable ripple through the fabric of space that reached instruments called LIGO more than 1 billion years after the event itself occurred. None of this, remarkably, requires the Sun's own story to end early. By the most recent solar models, the Sun is expected to remain a stable hydrogen-fusing star for roughly another 5 billion years past the present day, before swelling into a red giant large enough to engulf Mercury and Venus and possibly reach Earth's current orbit, meaning its own internal evolution, and the Andromeda merger are expected to unfold on broadly comparable timescales, two enormous, independent processes reaching their major milestones within a few billion years of one another. What comes after both, the eventual state of the merged galaxy and the far future fate of a universe still stretching apart at an accelerating rate, is the final layer of this whole picture, and it reaches conclusions considerably stranger than a single galactic collision. Return for a moment to the tug-of-war described several chapters back. Gravity winning decisively at close range, holding the local group and Laniakea together, while the accelerating stretching of space wins decisively at the very largest scales, carrying distant galaxy clusters apart from each other ever faster. Extend that contest far enough into the future, and it produces one of the stranger conclusions in modern cosmology. Galaxy clusters and superclusters that are not gravitationally bound to each other, meaning most of the distant structures beyond Laniakea's own basin, are expected to keep receding from the merged local group at increasing speed as cosmic time goes on, precisely because the accelerating expansion of space adds more stretching, not less, the farther apart two objects already are. Run this forward for a sufficiently long time. Current models suggest something on the order of 100 billion years, well beyond the roughly 13.8 billion years the universe has existed so far, and the consequence is that essentially every galaxy not already gravitationally bound to the merged Milky Way and Andromeda system will have receded far enough, and be moving away fast enough that its light will never again be able to reach an observer here, regardless of how sensitive future telescopes become. This is not a matter of galaxies simply becoming too dim to see, the ordinary limitation of distance. It is a stronger and stranger limit, a galaxy receding fast enough, carried by the accelerating stretching of space, can end up moving away from us faster than light itself can cross the growing gap, meaning no signal it emits after that point can ever complete the journey here, no matter how much time passes or how sensitive the instrument built to receive it. Astronomers describe this as galaxies crossing beyond a cosmological horizon, a boundary rather like the edge of a black hole's event horizon in its practical effect, though produced by an entirely different mechanism, the stretching of space itself rather than an object's intense gravity. Even today, the most distant galaxies astronomers have observed, seen as they were more than 13 billion years ago in light that has been travelling ever since, are already receding from us fast enough that they lie close to, or beyond, the boundary of what future observers here will ever be able to reach, a preview in the present of exactly the isolation this chapter is describing for the far future. What remains in this far future picture is the merged galaxy formed from the Milky Way and Andromeda, likely by then further merged with the local group's other bound members as well, existing essentially alone in an observable universe that has otherwise gone dark and empty of other galaxies, an island system surrounded by a vastly larger volume of space from which no further light will ever arrive. This has direct consequences for the motif that opened this whole exploration, the cosmic microwave background used to first measure the local group's motion at all. That ancient light is itself subject to the same relentless stretching that is carrying distant galaxies beyond view. Already redshifted enormously from its original state at 380,000 years after the Big Bang, it will continue to stretch as the universe expands, its wavelength growing longer and its effective temperature dropping ever closer to absolute zero, until in a sufficiently distant future it becomes too faint and too stretched for any conceivable instrument to detect at all. Future civilizations, should any exist by then, inheriting a night sky containing only the stars of their own merged galaxy, would have no direct observational evidence that the Big Bang or the expanding universe ever happened at all, the very evidence that made this entire chain of reasoning possible today having stretched itself permanently out of reach. It is worth being honest about how far ahead these particular predictions reach, considerably farther than the multi-billion-year timescale of the Andromeda collision itself, resting on the assumption that dark energy continues behaving the way it appears to behave today, across a length of time many times longer than the universe's entire history to date, an assumption current evidence supports, but cannot yet fully guarantee. Some alternative models allow for dark energy's strength to change over time, which would alter this ending in ways researchers cannot yet rule in or out. Even accounting for that honest uncertainty, the broad shape of the conclusion, a universe where gravity wins locally while the space between unbound structure wins globally, is well supported by the same physics responsible for every motion traced across every chapter of this account, from the spin of the Earth to the drift toward Laniakea. What that leaves, when every layer is finally stacked back together, is worth stating plainly. Stack every layer traced across this account back on top of each other, and the full picture of the Milky Way's actual motion comes into view all at once. Earth spins on its axis, carrying anyone standing on its surface at up to 1,670 kilometres per hour, depending on latitude, a rotation Leon Foucault proved directly with nothing more than a swinging pendulum in 1851. Earth simultaneously orbits the Sun at roughly 107,000 kilometres per hour, a motion Friedrich Bessel finally measured directly in 1838 by detecting the tiny parallax shift of a nearby star. The Sun, with Earth and every other planet in tow, orbits the centre of the Milky Way at roughly 230 kilometres per second, a single circuit, taking about 230 million years, held in that orbit partly by a black hole whose mass was pinned down by two research teams decades apart, and partly by the invisible dark matter halo Vera Rubin and Kent Ford's rotation studies first exposed in the 1970s. The Milky Way itself, along with its nearest large neighbour Andromeda and roughly 80 smaller galaxies, moves together as the local group, drifting at some 630 kilometres per second relative to the oldest light in the universe, the same faint radio hiss Arno Penzias and Robert Wilson stumbled onto by accident in 1965, pulled by the combined gravity of the Great Attractor, a genuine concentration of galaxy clusters roughly 250 million light-years away, hidden for decades behind the Milky Way's own disk. That pull sits inside a still larger structure, the Laniakea Supercluster, a basin of attraction spanning roughly 500 million light-years, and mapped for the first time only in 2014, itself possibly drawn toward an even more distant and more massive concentration called the Shapley Supercluster. None of these motions cancel each other out, or compete for the title of the real one. They simply layer, each one true at its own scale, exactly the way a person can be sitting still in a chair on a moving train, in a train moving through a country that is itself turning with the planet. The honest, complete answer to where the Milky Way is actually going is therefore not a single direction but a nested list of them. Gravity organising motion at every scale from a spinning planet up to a supercluster hundreds of millions of light-years wide, with an accelerating stretching of space, first measured by two independent teams of astronomers in the late 1990s, working in the opposite direction at the very largest scales of all. Somewhere inside all of that layered motion sits a single open pellet of light, The Sun, one star among 200 billion or more sharing the same galaxy, itself one galaxy among trillions across the observable universe, and every one of those countless points of light is caught up in its own version of exactly this same nested motion, spinning, orbiting, drifting, and eventually merging or receding, according to the same handful of physical laws that govern the Sun's own path. In roughly 4 to 5 billion years, that Sun, its planets almost certainly still intact and orbiting normally, will be swept up into the first stages of the Andromeda collision, its familiar flat spinning disk of a home galaxy gradually reshaped over billions of subsequent years into something new, an elliptical galaxy no human skywatcher the likeness of a reshaping the disk has, in a smaller way, already lived through once before in its ancient merger with Gaia-Enceladus. Far beyond that, on a timescale current physics can describe only in careful, appropriately hedged terms, the merged galaxy that results may find itself increasingly alone, its former neighbours carried beyond any possible horizon by the accelerating expansion that is already quietly underway today, and the ancient background light that first revealed all of this motion will have stretched itself beyond the reach of any future instrument. None of this was felt by anyone standing still on the ground while reading it. That, in the end, is the real answer to the question this exploration set out to ask. The Milky Way, and everything within it, has never once actually stood still, and the ground that feels so reliably fixed underfoot has been in continuous, layered, measurable motion for the entire 4.6 billion year history of the Sun that warms it. Strip away every layer, and the picture that remains is this: nothing in the universe is actually still, and nothing is moving alone. The ground under your feet turns with the Earth orbits the Sun, carrying Earth and every other planet with it, sweeps around the centre of the Milky Way once every 230 million years. The Milky Way itself, bound to Andromeda and dozens of smaller galaxies, drifts through the local group, which in turn rides the currents of the Laniakea Supercluster, itself flowing toward a concentration of mass so large it may be tugging on a meaningful fraction of the visible universe. Every one of those motions was invisible until someone found the right fixed point to measure it against, and every fixed point, in turn, turned out to be moving too. In 4 to 5 billion years, the pale point of light that is our Sun will be swept up into a new, larger galaxy formed from the collision of the Milky Way and Andromeda, its planets almost certainly undisturbed, its sky utterly rearranged. Far longer after that, in a universe stretched thin by its own expansion, that merged galaxy will likely stand nearly alone, its neighbours carried beyond the reach of any possible telescope, and the ancient light that first revealed all this motion will have stretched past the point where anything could ever detect it again. This is not the first time the Milky Way's disk has absorbed a smaller galaxy and come out the other side essentially intact. Roughly 10 billion years ago, in its own early youth, the Milky Way is thought to have merged with a smaller galaxy astronomers now call Gaia-Enceladus, an event whose fossil traces, clusters of stars still moving on unusually steep, elongated paths, remain detectable in the disk today. The coming collision with Andromeda is simply the next chapter of a process the galaxy has already lived through once before. We began by asking where the Milky Way is going. The honest answer is that it is going everywhere at once, at every scale, and has never for a single instant been standing still. Understanding that does not shrink the ground beneath your feet. It reveals what was always true of it, that the still, ordinary place we call home has been in motion since the moment it formed, has already survived one galactic merger, and will keep moving and merging long after we are gone.